Hello, my name is JuliannLamproe, and I have been working on the validation of nuclear data sensitivity calculations by the MC&P PERT card. I am mentored by Teresa Cutler and Michael Hua, as well as advised by Professor Pozzi at the University of Michigan. To dive into a little bit of motivation, predictive codes use nuclear data to simulate experiments. Improving the nuclear data improves the simulations and improves the results, causing higher fidelity designs and reduced costs. Therefore, improving the nuclear data is of the utmost importance. Nuclear data is improved via integral benchmark, which is where they compare simulated and measured quantities to derive recommended changes to improve the overall precision and accuracy of nuclear data. And then sensitivity quantifies how much a specific parameter, like multiplication, is changed by a perturbation of a contributing parameter, like cross-section or nuclear data in general. There is no direct tool to estimate sensitivity outside of the MC&P case-in card currently, which is only available for the effective multiplication factor. And additionally, this work validates a method of estimating other sensitivities that utilize the MC&P PERT card and tallies. For mission relevance, as I mentioned, sensitivity calculations will be used to create high-impact integral benchmark experiments to improve nuclear data, and improved nuclear data serves all users, which comprises the entirety of an NSA. For the MTV Impact, I took part in the MTV Nuclear Engineering Summer School, as well as some measurement campaigns and an internship at Los Alamos National Lab. Before I dive into the methods, I need to do a little bit of defining. So at the bottom of this slide, you can see the first order relative sensitivity coefficient in terms of cross-section and p sub x. And then I have the Taylor series expansion of some response or tally that is a function of some cross-section or any nuclear data expressed here and then simplified. And I can rearrange these terms to get the first order and second order response to be used in the estimations of sensitivity. For the PERT approach, it's important to note that it is limited to the cross-section perturbations, and additionally, each energy band and isotope require an individual PERT card, and these energy bands are the energy in which you want to perturb the cross-section. It is unrelated to the tally energy bands that you put in. And so for the PERT approach, you basically just make a fictitious material with its own name card in the file and make a fictitious weight fraction and density. And this goes into the MC&P PERT card. It doesn't go into any other place in the file. And method 2 gives you the change in response, and that can be used to calculate the sensitivity along with the unperturbed response. For the brute force approach, or the ground truth approach, where I am perturbing things manually, I obtain a compact INDEF file, which is just where all the cross-section libraries are, and I perturb it using this code called Friendly, which is a nuclear data processing system. And I collect the tally response from each file, and for each sensitivity estimate, you require 3 runs. You need the unperturbed case, a perturbation up, and a perturbation down, and each of those are individual runs. And then you can, once you've collected that data, you can do the sensitivity estimation using either the PERT equation shown on the left or the central difference theorem shown at the bottom right here. For some preliminary results, I have a 6 centimeter sphere of plutonium, a 2 centimeter natural copper reflector, and the response that I'm using here is the track length estimate of the cell flux on the inner sphere, and the multiplicity of this case is 1.0005. And I have a figure of the geometry just for clarification. And on the bottom, I have the energy versus sensitivity for this case using the PERT method, the Friendly or the brute force method using the central difference, as well as the PERT equation, just to compare, especially when I do the uncertainty analysis in the future to see which equation works the best. And as you can see at lower energy ranges, there isn't a lot of agreement, but as we approach 1 MeV, they start to agree very well. I think that the disagreement at the lower energy range has something to do with the lower energy bound of the perturbation systems that I'm using. Friendly and the PERT card have different lower energy bounds, and I think this could have something to do with the differences in the lower energy range. In conclusion, I think that the agreement of the PERT card and the brute force results prove the validity of calculating nuclear data sensitivities by the MCMP PERT card, especially at these higher energy ranges. I think the overall agreement will be a lot easier to understand once I've done the uncertainty analysis, which is definitely one of my next steps. In the future, I want to apply these two methods to more complex cases like the music measurements and scrap benchmark from Los Alamos National Lab. And then, of course, any new methods or MCMP tools can be compared to these methods for validation purposes. And then additionally, work after validation of everything, I would like to continue to find ways to calculate the sensitivity of even more parameters to develop even more high impact benchmarks for the improvement of nuclear data. And with that, I would like to conclude. So thank you for listening.